pairing up here, we'll see that chlorine, needing one more electron, will share with one of carbon's vacancies. So chlorine has its octet. Fluorine, one more to give its octet. So we'll see the fluorine, a chlorine, a fluorine, a chlorine. This now gives everybody their octet, and what we'll see is a chlorofluorocarbon being formed, known as CF2Cl2, as a gas. So to continue with covalent bonding, we see oxygen needing 2 more electrons for 8. Hydrogen has 1 electron available. So one hydrogen's electron can fill this empty space. Another one for this gives oxygen its octet. The 2 protons, remember hydrogen is 1 proton, 1 electron. The 2 protons of water, however, are positively charged on one side of the water molecule. So what can actually happen is with these lone pairs of electrons on oxygen, they can actually strip away one of the protons. This is kind of a reversal in order to create an ion that's pulling an electron away. Remember, pulling an electron away will create a negative charge where the electron goes, but now the positive proton here brings a positive charge with it. So when this happens in water, what we see is oxygen, more electronegative, keeps the octet of electrons. Hydrogen, on the other hand, the 1 proton, will actually be pulled away to another water. And what this results in is what's called the hydronium H3 plus cation in water, and the hydroxide OH minus anion in water. And this is what the pH scale is based on, the plus and minus charges in water. It's called the dipole nature of water. Now another type of bonding which actually occurs between molecules and not atoms is called the hydrogen bond, which is more specifically a proton bond, because what happens in water is a proton, being the positive portion of the water, can be pulled away by the electron pair, the lone pair of another neighboring water. So what happens now is when the electron pair grabs onto the proton of another water, this is what makes water stick together. And this is known as the hydrogen bond, but the proton bond is actually what's happening. So one electron pair grabbing onto a proton of another water makes these 2 stick together, and by pulling the positive charge to one side of the atom, it makes this other water more negative down here, which means it's going to grab onto the positive part of another water, which will grab onto the positive part of another water. And this is what makes water stick together. Okay, now still considering covalent bonding, some variations of the octet stop sign still show that these atoms will have octets, 8 electrons around them, but the covalent bonds will now be for oxygen, remember needing 2 more electrons for 8, will form a double bond. This is why oxygen is O2. For nitrogen, 3 vacancies, 2 nitrogens will get together to form a triple bond. 1, 2, 3 covalent bonds between them. This is one of the strongest bonds in nature, the triple bond of nitrogen. Okay, more covalent bonds occur when elements in group 3, they don't follow the octet rule at all. Aluminum or boron. In this example, aluminum forms what's called a trivalent bond, 3 bonds. But remember oxygen, it adheres to the octet rule, 2, 4, 6, 8 electrons on oxygen. But again, to make the trivalent of aluminum, being covalent bonds, we're sharing these pairs. So there's 2, 4, 5, 6 electrons. That's 3 bonds of aluminum. And now on oxygen in the middle, we see 1 lone pair, 2 lone pairs. That's 4, 5, 6, 7, 8, sticking to the octet. And here the other aluminum, 2, 4, 6 electrons, 3 bonds for aluminum. And boron forms the same way. This molecule here turns out to be alumina, aluminum oxide. More covalent bonds here, away from the octet now. Phosphorus, we'll see, can actually form 1, 2, 3, 4, 5 covalent bonds. This is 10 electrons, but oxygen here we'll see has 2, 4, 6, 8 electrons still. But even though it's not being bonded, this electron here, remember an electron has a negative charge. So with 1 here, 2 here, 3 here, it gives a 3 negative charge overall to what's called the phosphate anion. So covalent bonding here with 5 bonds for phosphorus, and the oxygen still adheres to the octet. Now phosphorus is known to do some strange things, because what we can see is that phosphorus can form 3 bonds, as in phosphorus trichloride, or it can form 5 bonds. So what we'll see happening is this lone pair of electrons, there's 2 electrons there, will actually begin to split up, and as it splits up, we'll see, remember the covalent nature of bonding is an electron wanting to pair up. Well, if these become unpaired, what happens is now it's available to form 2 new bonds. So if we picture chlorine bonding to each one of these, it would be 1, 2, 3, 4, 5 bonds. This is phosphorus pentachloride. So phosphorus can form between 3 or 5 bonds, all in electron pairs, covalently. Following again the idea of the electron pairs splitting open to form new bonds, sulfur is underneath oxygen in the periodic table. With 2 lone pairs of electrons, sulfur can now form 1, 2, 3, 4, 5, 6 bonds. Oxygen, remember the octet, sticks to that rule of 2, 4, 5, 6, 7, 8. Sulfur now, though, 1 covalent bond, 2, 3, 4, 5, 6 covalent bonds now. And what happens, remember hydrogen, 1 proton, 1 electron? The 1 proton will actually be pulled away by water. This is what makes sulfuric acid a strong acid. The proton leaves the electron behind because oxygen's more electronegative. So with an electron, negative charge on this oxygen leaves a proton with its positive charge being able to be taken up by water. And this happens in 2 places on the sulfate anion. So 1H, 2H leaving is a sulfate anion, and 2 protons in water, making sulfuric acid a strong acid. To show covalent bonding again, sodium bicarbonate, hydrogen will actually stay covalently bonded to an oxygen, but sodium will become ionized in water. So sodium gives up its electron to fill oxygen's 8th shell. So we have 2, 4, 5, 6, 8 electrons for oxygen, but there's a negative charge out here on this oxygen. This hydrogen stays bonded covalently, this oxygen with its octet. Carbon, notice the octet, 2, 4, 6, 8 electrons, and oxygen here, 2 bonded to carbon, 4, 6, 8 electrons. Sodium bicarbonate is known as baking soda. To now show how covalent bonding can form long chains and polypeptides, see carbon, again with the octet rule, will have 2, 4, 6, 8 electrons around it. But this carbon to nitrogen bond is what's called a peptide bond, and this forms between amino acids. So we see with nitrogen octet, we have a lone pair here, which would kind of give a negative charge out here. 2, 4, 6, 8 electrons around that. So this is what's called the backbone, the amino acid backbone, forming through peptide bonds between nitrogen and carbon. So now a nitrogen to carbon bond, this isn't a peptide bond. We see what will happen on this carbon can now form a chain. And this is called the amino acid side chain. And we see this really shows the octet, because see something like carbon here will have 2, 4, 6, a double bond to another carbon, 8 electrons. This carbon, 2, 4, 6, 8 electrons. Bonded to nitrogen, 2, 4, 6, 8 electrons. See how important the octet becomes. Here with a double bond to carbon again, 2, 4, 6, 8 electrons. This carbon here, 2, 4, 6, 8 electrons. So this now shows that an amino acid side chain, tryptophan, can be hanging off the end of this carbon, which is then bonded through a peptide bond, up to where another amino acid side chain could be hanging off. This is how amino acids form proteins by the polypeptide bonds forming proteins.